guys, welcome back. Here's the last video clip for chapter 11 pertaining to what we call Hoff Factors, and it's section 11.7ish, I think. Yeah, check it out. I think it's 11.7. I called it an ideal perhaps because this is the theory and the measurement never always exactly matches up with what we're looking at. Well, it does sometimes, but in any case, when I'm dissolving a salt in the water, it breaks up into ions, and those plus minus ions, of course, they each contribute to the effects we've been calling the colligative properties, or changing some of the properties of the solvent as it becomes a solution. So examples, here's the Hoff factor of 1, where I don't break up at all. I just have 1 mole of this dissolving to give 1 mole, and 1 mole of that sugar, and then 1 mole of this alcohol dissolving to give 1 mole of the alcohol. Here's the Hoff factor of 2, where I have sodium chloride. 1 mole of sodium chloride solid would dissolve in water to give 1 mole of sodium ions, 1 mole of chloride ions, total of 2 ions. There's 1 ion there and 1 ion there. 1 mole of ammonium fluoride solid in the water would give 1 mole of ammonium ions, 1 mole of fluoride ions, total of 2 moles. So when these ionic substances break up, they might give 2 moles of particles for every 1 formula unit, and that doesn't matter if it's plus 2, minus 2, plus 1, minus 1. It just is a raw number of ions. So here I have 2 moles of ions for every mole of magnesium sulfate, or 1 mole of hydrogen iodide gas gives 1 mole of hydrogen ions, 1 mole of iodide ions, hydriodic acid in the water. But again, the Hoff factor is 2. Or the examples continue. A Hoff factor of 3. 2 chlorides and 1 calcium. Calcium chloride in the water, or solid, dissolve it in the water. You get 1 calcium ion, 2 chloride ions, total of 3 ions. 1, 2, 3. 1, 2, 3. And 1, 2, 3. 1, 2, 3. Doesn't matter what the charges are, the numbers in front. 2 sodiums here, 1 sulfide there. So this is going to give me 3 times the colligative effect as I would think with just, say, a sugar or an alcohol or some other molecule that's not breaking up into ions. It's the raw number of ions that affect the extent or degree of colligative effect. N equals 5, vanadium chloride. This is called vanadium 4 chloride because it has a 4 plus charge on the vanadium. Got to have 4 counter ions to balance it, but there's 4 ions here, 1 ion here, total of 5. 5 for the Hoff factor. What if I had a 0.11 molar iron 3 chloride solution? Well, when that dissolves in water, can you see I've got 3 chlorides here and 1 iron? Hoff factor is 4. In essence, I take that 0.11 times 4 to find the total number of particles in the water. Similarly, 0.21 molar sodium chloride. I have 0.21 molar sodium ions, 0.21 molar chloride ions. If I had ways to measure the sodium or the chloride, I hopefully could measure it exactly to that. But the total number of ions in the water, double it. Hoff factor of 2. Hoff factor of 3. 1 copper, 2 iodides. So 3 times that number, 0.093 is the bottom line. But I would have 0.031 molar of copper and 0.062 molar of iodide. Total, add them all up, 0.093. Trick question. Sugars and alcohols and molecules that dissolve in the water that don't break up into ions still have just that same molarity. Here's a really tricky one. Weak acids and weak bases. Weak acids and weak bases only break up a little bit in water. If I had a 0.1 molar vinegar solution, as I'm showing here, 0.1 mole, this is vinegar, 0.1 molar vinegar solution would break up in the water, but only a teeny bit. You see the 3% there? I have to break out some equilibrium constants, also dependent on temperature. But I'm going to have more than 0.1 molar, but less than 0.2 molar. If this broke up totally, if this molecule broke up totally, it would be called a strong acid. And I would have 0.2 molar of ions, but I don't because it's a weak acid. This is very difficult to calculate. The Hoff factor is not 1 because it doesn't stay together totally, but it's not 2 because it doesn't break up totally. I don't know, 1.1, 1.05. have to break out some more detailed calculations, not for today. Our text mentions the definition of Van Hoff factor as the number of particles in solution divided by the moles of solute dissolved. That's one way to think about it. But I just tend to look at the ions. If it's an ionic substance breaking up into ions, how many ions are you going to break up into? Now this ideal doesn't always meet the perfect, doesn't always come to play in reality. So I have one sodium ion, one chloride ion, one sodium ion, one chloride ion, Van Hoff factor of 2, one sodium ion surrounded by water, one chloride ion surrounded by water. But even if this is surrounded by water, it still has some negativity to it. And even if this is surrounded by water, this region still has some positivity to it. And this region may still be attracted to this region, positive, negative, and they may chum together, hang out a little bit together for a little while, glom onto each other. So some ions may momentarily be attracted to each other even though they're solvated and surrounded by water. And this leads to the measured Van Hoff factor to be a little bit less than the ideal. So here are my ideal Van Hoff factors. I just threw it in there for entertainment purposes to confuse you because sucrose is just a 1, doesn't break up into ions. But look at the 2 is really measured as a 1.9 and the 3 is really measured as a 2.7. So some of those ions in the magnesium chloride solution, even though they're surrounded by waters, are still attracted to each other and so don't maybe totally contribute a Van Hoff factor of 3 like we would think they would, could, should. And this is totally measured and we have no way to calculate it, or there's not a very good way to calculate it easily. And so, also these are dependent on the concentrations of these in the water. So more dilute, more concentrated, that would also affect what I observe or measure for my Van Hoff factor over there. How do the equations for the colligative properties change? Freezing point depression, boiling point elevation, osmotic pressure. You probably recognize those equations, except now there's an I thrown in there. I times the molality, I times the molarity. Here's an example. So in addition to the molalities and the molarities, the mole fractions could also possibly change. What if I was trying to do a vapor pressure calculation with the mole fraction of solvent in a 50 grams of sodium sulfate dissolved in 200 grams of water? Well, I calculate the moles of sodium sulfate, but since the Van Hoff factor is 3, I went ahead and took it times 3. And then I would say, if that was in 200 grams of water, 11.11 moles of water, my mole fraction of water, which is saying how much of my mixture is water, 0.913, is dependent not just on the molarity or the moles of sodium sulfate, but I have 3 ions, so I took that times 3, took it times 3, and all those moles are included in my mole fraction. And if I bothered to look up the vapor pressure of water at whatever temperature I'm talking about, I can multiply it by 0.913 and say that these particles occlude or interfere with the evaporation or the vapor pressure of the water to this degree right there. 50 grams of, back to a similar question, 50 grams of sodium sulfate, 0.325 moles of this salt, but the number of particles is actually 3 times larger. Let's say, for the sake of argument, 50 grams of sodium sulfate is 0.352 moles, and it's in 2 kilograms of water, 0.2 kilograms of water. The molarity would be 1.76 molal sodium sulfate. But at some point I need to multiply by 3. I could have taken this number, 3 times 0.352, that gives me the moles of solute particles. I could have taken that and divided it by 0.2 kilograms, and that would have straight away given me the 5.28 molal. Or I could say this is the moles of sodium sulfate, take it times the Van Hoff factor, I times molality, and that gives me the 5.28 molal. Then I could go about calculating the delta TF delta TB. Oh, I did it right here. So how would the change in freezing temperature be different? Change in freezing temperature with that I thrown in there? Well, this is old. I've been practicing with that for quite some time. But if I have a salt like sodium sulfate, 2 sodiums, 1 sulfate, but a factor of 3, this is 3 times larger of a change of a depression. Water usually freezes at 0, so now it freezes at negative 9.28 or negative 9.82. Oh goodness. So my salts breaking up into ions can definitely create a more dramatic effect in the colligative properties. Thanks for watching, guys. See you in class.